Another cyclist pedals the same bike at a rate of 1 revolution per second. Make a table showing the height of the bicycle pedal at times 0, 0.5, 1, 1.52, 2.5, and 3 seconds. So just like the previous example, we're making a T-chart with those times, those exact same times. So I'll redraw my T-chart here. But now this cyclist is pedaling at a rate of 1 revolution per second. So at 0 seconds, the pedal is still at the top at 18 inches off the ground, but he's pedaling twice as fast. So if it goes 1 full revolution every second, he's going to get to the quarter mark, not at 0.5 seconds like the other cyclists, but at 0.25 seconds. The bottom he will reach at 0.5 seconds, and he'll make 3/4 of a turn at 0.75 seconds, and then back up to the top after 1 second. So still going to be 18 inches off the ground at 0 seconds, but at a half second, so following it along, at a half second, he will now be at the bottom. 4 inches, that pedal would be 4 inches off the ground. And then after 1 full second, that's 1 full rotation, so the pedal will be back at the top at 18 inches. So every half second, it's going to switch from being at the bottom, or 4 inches, to back at the top at 18 inches. And at 2.5 seconds, it'll be back down to 4 inches. At 3 full seconds, back at the top at 18 inches. So I'm going to graph that on the same intervals. So 0, 18, and then 0.5 seconds, 4, it's going to be right here. 1.0, 18 seconds, so again, it's back up to the top. 1.5, 4. 2.0, 18. 2.5, 4. And 3.0, 18. So down, make kind of a smooth transition, then back up. And back down, and then back up, and back down, and back up, and it continues to make that same pattern over and over and over again. So this time the cycle is a little bit shorter. It has a period of 1 second. And if you compare that to the other graph, notice the other graph was a little bit wider with the cycle of 2 seconds, and this appears to be much more horizontally compressed with the cycle of only 1 second. And notice that this is 3 full cycles. Since it repeats itself every 1 second, and we've done from 0 to 3 seconds, that is 3 full cycles. The exact values of cosine and sine for the special angles are shown on the unit circle at the right. The cosine values are the x-coordinates of the points of the unit circle, and the sine values are the y-coordinates, as we learned from the very first part of this video. You do not have to memorize this circle, this unit circle. This is just going to be used to help introduce you to what a sine function looks like, or what many trig functions look like. Because the first thing we're going to do is, using this unit circle, we are going to graph the parent function of sine of x. So f of x equals sine x. So from the beginning of the lesson, we learned that each point on a unit circle is in the form of cosine sine. So all I need to do to figure out the values of each of the special degree angles from our special triangles is look at the y value around the unit circle, and that's going to be the sine of each of the values I need. For example, starting at 0 degrees, which is right here, if you look at the unit circle, 0 degrees, the sine of 0 is going to be this value, this y value right here, which is 0. So I'm going to go ahead and graph that. At 0 degrees, the value of sine is 0, so it puts it right there at the origin. At 30 degrees, the sine of 30 is 1/2. So I will graph 30, 1/2. So 30, 1/2 is over, I'm going by 15s on the x-axis, And each block is 1/4 of a unit on the y-axis, so that is 30 degrees, 1/2 of a unit tall. Our next special angle is 45 degrees. So 45 degrees is the square root of 2 over 2. That is approximately 0.70. So I will go over to 45 and up to 0.70, which is not quite to the third block, because the third block would be 0.75, so roughly here. And then at 60 degrees is my next angle in this picture. 60 degrees is the square root of 3 over 2. That is approximately 0.86. So I'll graph 60, 0.86, which is about here. Not quite halfway to between those blocks. And then finally, our next special angle is a quadrantal angle at 90 degrees, and the sine of 90 degrees is 1. So over to 90, up to 1. Continuing around, 120 degrees is square root of 3 over 2, which you already know from the 60-degree angle is about 0.86. So if I go over to 120, it should be about 0.86, which is the same height as what I was at 60 degrees. And then continuing around the circle, the next angle is 135. That's back to the square root of 2 over 2, which is about 0.70. So about right here, the same height as the 45. 150 degrees is back to a half. That's easy enough. And then we have a quadrantal angle at 180 degrees, and the sine of 180 is 0. So it does look like that we've done one full cycle because we're back to the x-axis, which is where we started at 0, 0. However, if we continue forward, we can see that if we go to 210 degrees, the sine of 210 is negative 1/2. So if I go over to 210, I'm going down to negative 1/2. And you can see that it's actually now going into the negatives. Sine goes into the negatives in quadrants 3 and 4 because the opposite sides are negative. So we actually haven't seen a full cycle yet. So we have to continue around the circle. So at 225 degrees, it's negative square root of 2 over 2. Which will be negative 0.7 approximately. So that would be about right here. And then at 240 degrees, it would put us at negative square root of 3 over 2, which is about negative 0.86. And we can continue to go around the circle, and I'm going to go ahead and flash forward all the way to 360. And there's the rest of the points. And that we have completed one full cycle. I'm going to go ahead and draw, connecting those points together with a nice smooth curve. And there you go. That is one full cycle of the parent function for sine. After it gets to 360, the cycle is going to repeat. So since it goes around the circle, we know that, let's say that we know that a 420-degree angle is the same as a 60-degree angle because they are coterminal. So whatever we have for 60, we would have for 420. So we could say that's right here, and it could just continues that same cycle as long as we want to make it. Finally, a little bit of review. We can evaluate trig expressions, again, using reference triangles. We can find the exact value of each expression, the cosine of 480 degrees. So if I look at the cosine of 480 degrees would be a full 360 degrees plus 120 degrees past that, which would put my terminal side right there with this reference triangle. And that would be a 60-degree angle right here. And so then since that's a 60-degree angle, the measure of the adjacent side would be -1. Since we are going to the left on the x-axis, we are still rising. So the opposite side would be the square root of 3 with a hypotenuse of 2. So the cosine of 480 degrees would be the adjacent side of -1 over the hypotenuse of 2. Part B is 11 pi over 4. If you want to change that to degrees, you would take 11 times 180 divided by 4, and that would give us a 495-degree angle. So that would be a full lap. That's 360. Another 90 degrees would put us at 450. So we're going 45 degrees past 450, which means we are 45 degrees short of hitting the x-axis. So that is a 45-degree angle. So this is our 1, 1, square root of 2 triangle. It will be -1 on the x-axis. But sine formula is opposite over hypotenuse, so it would be 1 over the square root of 2, but we should rationalize our denominator by taking it times the square root of 2 over 2, which means the sine of that 495-degree angle would be the square root of 2 over 2, which is what we just figured out, the sine of 11 pi over 4, because 11 pi over 4 is equal to 495 degrees.